I've recently become quite addicted to this game called Flow Free. The game was released in early 2012, which is when I first started playing it, but 10 years later I picked it up again and remembered how enjoyable it is. Flow is a puzzle game. You are presented with a rectangular grid of cells, some of which have a colored dot within them. The player's goal is to connect every pair of dots of the same color through a sequence of adjacent cells, such that the paths do not intersect one another, and every cell of the grid is visited exactly once. Different levels feature larger and larger grids, thus making the game harder and harder. But really, how hard is this game? In this video, we will explore the story behind the game, delve into the hidden mathematics, and quantify how difficult this game may be. The first appearance of a flow-like game was seen in a newspaper called the Brooklyn Daily Eagle in 1897 by a man named Sam Lloyd. Lloyd was a chess player, mathematician, and most importantly, a puzzle composer. You may have seen some of his other puzzles, such as the Trick Donkeys problem. And also maybe the Vanishing Area puzzle. Flow was popularized in Japan by the Japanese publishing company Nikoli, who also happens to be responsible for the popularity of other puzzles, such as Sudoku. The Flow puzzle was published under the name NumberLink. So how hard are these Flow puzzles? Well, if you ask me, not very hard. Maybe a better question is, what does it mean for a puzzle or problem to be hard? We'll dive into this in just a bit. For now, we need to understand the game a bit better. It turns out that there are 3 versions of Flow. In the first version, a player is supposed to connect all pairs of terminals via non-intersecting paths, but the player need not visit all of the cells of the grid. In the second version, a player now has the requirement of visiting all of the cells of the grid. In the third version, the player must visit all cells of the grid. However, this version also allows paths to take unnecessary turns. That is, a correct path may have more turns in it than a shorter viable path. For the sake of this video, we will mainly be focusing on the first and second versions of the game. One strategy to help simplify the game is to focus on corner and edge cells. Take a look at the bottom left cell. Some path must go through this cell. But it seems like any path that reaches this cell would enter through the right and then get stuck at this corner with nowhere to go. Except for the orange path, which will exit through the right. Because of this observation, we can rule out the natural vertical path connecting the orange terminals, and instead conclude that the orange path must wrap around. But this is just a tip, and still doesn't answer how hard the game is. Let's ask a different question. How would we determine if an instance of a flow puzzle has a solution? Perhaps the most naive idea would be to brute force a puzzle and try all possible paths until a solution is found. But is there a better solution? Maybe not something immediate. To answer this question, we must do a deep dive into the world of complexity theory. Complexity theory deals with the issue of classifying problems based on how difficult they are to solve. Suppose you had a group of people, and you first wanted to figure out who was the oldest person in the group. This is an easy problem to solve, because you can just go through each person one by one, ask them their age, and choose the largest value. Now suppose you wanted to determine if there is a subset of half of the people, such that every pair of people within the subset are friends. This problem has no immediate solution outside of brute force. Complexity theory allows us to place these two problems into different classes. This is the class P. Problems in this class are problems whose solution can be found in polynomial time. Let's not worry too much about what this means. You can just treat this as problems that can be solved quickly, like finding the oldest person in the group. This is the class NP, which stands for non-deterministic polynomial. Problems in NP are problems whose solution can be checked in polynomial time. For example, the problem of determining pairwise friends. To elaborate on what it means to check, had I provided you the names of half of the people who I think are all pairwise friends, you could quickly verify whether or not this is a solution by asking every pair of people whether or not they are friends. Within the class NP is a grouping of problems called NP-complete problems, the set of problems considered to be the hardest in NP. A problem is NP-complete if any problem in NP can be reduced into the NP-complete problem. Equivalently, a problem is NP-complete if a different NP-complete problem can be reduced to the problem at hand. We'll touch on what the word reduce means in just a bit, but back to the complexity classes. There are a lot more classes, including BPP, PSpace, and EXP. We won't go into the details of these classes, but I merely wanted to highlight the vastness of complexity theory. The class NP is considered to be a modern-day wonder. For decades, academics have been trying to determine if the class P is equal to the class NP. In other words, is there a single NP-complete problem that also belongs to P? If so, then P equals NP. Today, we are going to show that flow is NP-complete. To formalize the situation, given an instance of flow, determining whether or not a solution exists is an NP-complete problem. To prove this, we must do two things. First, we must prove that flow is in the class NP. Then, to show that it is NP-complete, we will perform a reduction from an existing NP-complete problem to flow. To proceed with this proof, we need to represent the flow problem as a more mathematical entity. To do this, we're going to use a graph structure. The vertex set is going to be the cells of the flow grid. Edges between vertices will exist if and only if the cells represented by the vertices are adjacent. Next, we will have a set of pairs denoted T, where each pair denotes terminal vertices. That is, a pair of vertices that must be connected. Lastly, we say that an instance of flow has a solution if there are a set of paths in the graph connecting each pair of terminal vertices in T such that the union of all paths touches all of the vertices exactly once. This corresponds to all cells being visited in the grid representation. Great, now we can go about showing flow is NP-complete. First, we must show that it is in NP. Recall that NP is the set of problems whose solutions can be checked quickly. A solution to a flow problem would be a set of paths. To verify the solution is correct, we need to make sure that all pairs of terminals are connected by the paths, that every vertex in the graph is visited exactly once, and that edges between vertices on the path exist in the graph. Checking the terminal pairs can be easily done by looking at the start vertex and end vertex of each path. Checking vertices can be done by simply traveling through each path and checking off which vertices are visited. Checking edges can be done similarly. The second part of showing flow is NP-complete is performing a reduction from an existing NP-complete problem. Let's now discuss what a reduction is. A reduction is essentially a transformation of one problem to another problem. More formally, problem A reduces to problem B if we can represent an instance of problem A as an instance of problem B, such that if problem A has a solution, then problem B has a solution. And if problem A does not have a solution, then problem B does not have a solution. There's an extra restriction that we want these transformations to be polynomial reductions, but this detail can be ignored for now. We will be performing a reduction from 3-sat to flow. 3-sat is a well-known NP-complete problem, but the proof for why it is NP-complete is long-winded and can be saved for another video. 3-sat asks whether or not certain Boolean formulas can be evaluated to true. let's take a look at some definitions. A literal refers to an instance of a Boolean variable or a negation of a variable. A clause refers to a set of literals that are combined via logical ORs. We say that a Boolean formula is in conjunctive normal form, or CNF, if the formula is a conjunction of clauses, that is, clauses that are combined via logical AND. The 3 and 3 sat means that each clause can have at most 3 literals. The formula phi is thus in CNF form. In Boolean logic, an OR evaluates to true if at least one of the arguments is true. A logical AND evaluates to true if all of its arguments are true. We say that a formula is satisfiable if there exists an assignment of variables so that the entire formula evaluates to true. Here, phi is satisfiable because we can let x1 equal true, x2 equal false, x3 equal true, and x4 equal true. You'll note that for phi to be satisfiable, every single clause must evaluate to true. Now we are ready to perform the reduction. It's helpful to remind ourselves of what we are trying to do here. We want to come up with a general-purpose, quick procedure that takes any 3-sat formula and provides us an instance of the flow problem such that the formula is satisfiable if and only if the flow problem has a solution. The flow problem that we will reduce to is version 1 of the game, where not every vertex needs to be visited, but the paths need to be non-intersecting. With this in mind, we should be considering an arbitrary 3-sat formula and not something specific, as our graph construction should be generalizable. Let's now perform the reduction. For each distinct variable that appears in phi, we will create 2 vertices, as shown with x1 and x1 prime, for example. And these 2 vertices will be connected by 2 distinct paths. We'll include these vertices as a pair in our terminal set as well. Then, for each clause, we will similarly construct 2 vertices, and these vertices will be connected by 3 distinct paths. We will also include these vertices to the terminal set. Let's take a look at the variable vertices. Since we have included them in our terminal set, they must be connected by a path. There are 2 paths we could choose. A high path, which we will have corresponding to the variable being assigned true, and a low path, which will be when the variable is assigned false. The clause vertices are also in the terminal set, but each pair of these has 3 paths between them, one corresponding to each literal within the clause. Ideally, choosing the leftmost path will correspond to the first literal being true, the middle path will correspond to the second literal being true, and the rightmost for the last literal being true. It may be unclear how this relates to 3-sat, so let's take a closer look at phi, and suppose we had this satisfying assignment. With this assignment, we'll choose the appropriate paths connecting the variable vertices. Now, since this is a valid satisfying assignment, when we substitute into phi, we can see that there is at least 1 literal in each clause that evaluates to true. This will indicate that we can choose corresponding paths for our clause vertices. For a formula that does not have a satisfying assignment, there would exist a clause that does not have a literal being true. In this case, we would not want to be able to choose a path between the clause vertices. But how do we impose a restriction on whether or not to choose a path? Recall that our paths must be non-intersecting. So, if we add vertices between the paths, we add in some restrictions on what can and can't be chosen and when. First, we will rearrange our graph. The procedure for introducing vertices will be as follows. Take the first variable of the first clause and find the grouping of 6 intersections. Since it is the first variable of the clause, we'll focus on the leftmost clause path. If the variable is not negated, as x1 is, we will add a vertex to the bottom variable path. Now we'll look at the second variable, x2, and find its set of 6 intersections with c1. We'll use the middle clause path since x2 is the second literal. Since x2 is negated, we will add a vertex to the top path. For x3, it is unnegated, so we will add a vertex to the bottom variable path and the rightmost clause path. And we'll do this for all literals for all clauses. Please note that all other intersections between edges do not have a vertex at the intersection point, besides the vertices we added. We claim that this graph construction will have a flow solution if and only if the 3-sat formula provided is satisfiable. We've done a bit of justification of why this may be true, but a bit more is probably desired. Let's take a look at the high and low paths for x1. Both of these paths have one additional vertex on the path. The vertex on the high path corresponds to the negated x1 in clause 2, and the vertex on the low path corresponds to the unnegated x1 in clause 1. Suppose we were to choose the high path for x1, meaning that x1 will have the assignment true. Since the high path contains vertex n210, then we would be unable to choose the leftmost path connecting C2 and C2', because then the two paths would share a vertex. Note how n210 corresponds to the first literal of the second clause being evaluated to false, since x1 is negated. Instead, suppose we chose the bottom path for x1, meaning that x1 is assigned false. Now, for C1 and C1', we cannot choose the leftmost path because of n111. Again, note that this vertex corresponds to the first literal of the first clause being false. With this, we can see that if a literal evaluates to false, then the corresponding clause path cannot be chosen. Further, if all 3 literals within a clause are false, then we cannot choose a single clause path, which is an issue since the clause vertices are in our terminal set. But what happens when all literals in a clause are false? Then the entire clause is false, and then the entire 3-sat equation is false. This shows that if a 3-sat formula is not satisfiable, then there is no flow solution. If our 3-sat formula is satisfiable, then there will be at least one literal that is true in each clause, giving us a flow solution. So now we've answered the question. Flow is an NP-complete problem. It's pretty hard. Some of the eagle-eyed viewers may have observed that the paths we chose to connect the terminals in the graph we constructed do not visit every vertex. You are correct. We've shown that the first version of flow is NP-complete, the version where you need not visit all vertices. Credit to this paper by James Lynch for the proof that was presented. If you're wondering about the second version, where the player must visit all vertices, it is also NP-complete. The proof is done similarly to what I had just presented, with noticeable modifications. The paper including the proof is written entirely in Japanese, so I was unfortunately unable to read it. And it turns out that, unsurprisingly, the third version of flow is also NP-complete. Other viewers may be saying, hey, the graph we constructed looks nothing like a flow game board. This is true. One of the major differences is that the graph we constructed is not necessarily planar, whereas flow game boards are planar graphs. It can be proved that we can modify the graph we constructed so it is planar, and the proof remains complete. So what do we conclude from all of this? Flow is just as hard as 3-sat and the friend subset question. It seems like our best bet at determining if a puzzle has a solution is to utilize brute force, and that will remain true until someone comes along and changes the landscape of complexity theory forever.